Hello everyone, welcome to the spin tangle. Today it's a new topic that is called ideal Fermi gas at 0 Kelvin. Okay, this lecture is truly focused on the Fermi-Dirac statistics. Okay, let me introduce what is Fermi-Dirac statistics. It was introduced by the eminent scientist named Enrico Fermi. On his name, the statistics is further named Fermi-Dirac statistics. Okay, Enrico Fermi and it is Paul Dirac. Okay, so first let's understand what is what is Fermi gas. Okay, what is Fermi gas? I have written here Fermi gas. So what is Fermi gas? Fermi gas is an assembly of fermions. Okay, what are fermions? The particles having half integral spins. Okay, say half spin, 3/2 spin, 5/2 spin. Okay, these are the spin values of the particles, and this is Fermi gas is an assembly of fermions. Okay, this is nothing but this is nothing to deal with gas. The term gas used because of we are dealing with a statistical system, that is a huge number of particles are present in the system. Okay, so we know the distribution function is written as distribution function is written as f of e equals to number of particles at a certain energy level and the degeneracy of the energy level. Okay, this is the definition of the distribution function, that it says that the distribution function is the ratio of the number of particles present in a certain energy level to the degeneracy of that energy level. Okay, say you have an energy level E energy, say it is E energy level, and it has degeneracy G, and there are n number of particles present in the state. Okay, therefore the distribution function will be written as the number of particles upon the degeneracy of the level. Okay, and both will be the function of the energy. Okay, so this is, and it is written as, in case of Fermi-Dirac statistics, you have to remember 1 upon e to the power alpha plus beta e. Here it is a plus 1. In case of Bose-Einstein, this plus symbol is replaced by minus symbol. Okay, because why this is? Because the number of particles in case of bosons is greater and the number of particles in case of fermions are smaller. Why this happens? This plus sign is the reflection of the Pauli's exclusion principle, because all of the particles are fermions, sir. All of the particles are fermions. Fermions means, say, electron. Okay, we know the fermions obey Pauli's exclusion principle. Okay, Pauli's exclusion principle. What is Pauli's exclusion principle? That in case of half spin particle, no two particle can occupy, not more than two particle can occupy the same energy state. Okay, if one has up spin and second has to be the down spin, that is, this is called plus h cut by 2, having this is angular momentum, this is minus h cut by 2. I am not going to the quantum mechanical description of this thing. Okay, say spin half. If you have 3/4 spin 3/2 particles, say you have some particles that has spin 3/2, then what is the Pauli's exclusion principle for them? Okay, you have to look at that spin degeneracy, that Gs equals to 2s plus 1, that becomes 3 plus 1, that equals to 4. That means there can be maximum 4 particles can be in a certain energy state. Okay, depending on the depending on the spin values. Okay, depending on, I'm not going to that fact. Okay, Fermions obey Pauli's exclusion principle, and in case of distributing bosons, we do not have any exclusion principle like this, and the number of particles here increases. So here it is a minus sign in case of bosons, and in case of fermions, the total number of particles are restricted by the Pauli's exclusion principle. So we have to introduce a plus sign here. Okay, you know the if denominator is heavy, therefore the total value will be less than the previous. If denominator is not so heavy, therefore the total value will be higher. Okay, so we know one thing. I am writing this distribution function again. So distribution function in case of Fermi-Dirac statistic, FD, Fermi-Dirac statistics. What is this? Is equals to 1 upon e to the power alpha plus beta e plus 1. This is the required distribution function for Fermi-Dirac statistics. Okay, you have to remember this. Okay, now I am moving that. What is alpha here? Alpha is equals to minus mu upon kt. We know it from the Bose-Einstein statistics. Okay, in case of Bose-Einstein statistics, we have dealt with this thing, that alpha is equals to minus mu by kt. Here in Fermi-Dirac statistics, mu is equals to E Fermi. Okay, this is called Fermi energy. This is called Fermi energy. Okay, what is this? You know this is what? This is called chemical potential. Okay, chemical potential. This is a kind of potential energy in case of a chemical reaction or any kind of chemical transitions. Okay, so this is a energy term. Okay, so in case of Fermi-Dirac statistics, this energy term will be replaced by the Fermi energy. So the expression for Fermi energy will be what? Say writing is it's epsilon. Okay, because I'm writing this epsilon. I used to write this thing like this. Okay, so now we have to write this distribution function again by putting the EF value in case of mu here. Okay, so what will be here? E to the power, what is alpha? Alpha is equals to minus mu by kt. Therefore minus EF by kt, and here it is a beta E. Beta means what? Beta is equals to 1 upon kt. Okay, therefore here will be a E by kt term. Okay, plus 1 E by kt. This is on the power. So writing this thing carefully, that f of E equal to what? 1 by e to the power, take this kt out from the bracket, so 1 upon kt E minus E Fermi plus 1. Okay, now this is the distribution function. This is the final distribution function. I will be saying that this is the final distribution function in case of Fermi-Dirac statistics. Okay, remember this thing. This is FD distribution function. Okay, now remember this thing. Now I am moving from this Fermi distribution at T tends to 0 Kelvin, that is at absolute 0. Okay, this is our interest. In case of Bose-Einstein statistics, we were proceeding towards the 0 Kelvin temperature, and in case of Fermi-Dirac statistics we also have to proceed towards the 0 Kelvin one, and we have to check the nature of the system. Okay, this is absolute 0. So what we have to do here, first write down the distribution function. F of e will be what? 1 by e to the power, I think it is 1 by kt e minus e Fermi plus 1 if t is equals to 0. Okay, if t tends to 0 Kelvin, then put 0 Kelvin here, put 0 Kelvin here. Okay, by putting 0 Kelvin here, what we can see, if E is greater than EF, that is our energy is greater than the Fermi energy, therefore the numerator will be positive and the denominator is 0. Numerator will be positive and denominator will be 0. Something positive by 0 will be what? Something positive by 0 will be, I am writing this thing here, just wait for a while. F of E will be what? 1 by just wait, 1 by e to the power some positive value. I am writing this thing e minus ef positive value. I am doing this for this case. Okay, by 0 plus 1. Something by 0 is what? Infinity. Therefore here will be a 1 by e to the power infinity plus 1. 1 by e to the power infinity plus 1 becomes 1 by infinity, that equals to 0. Okay, it is for e is greater than ef case. Okay, remember this thing. Okay, this is our first point. Okay, this is our first point. I am say this is a, I am giving this a. Now I am moving to the second point. In our second point, if I am writing here it, if EF is greater than E, that means the numerator is negative. Okay, and we have considered that our temperature is 0 Kelvin. Okay, so I am writing this thing, f of E, our distribution function will be EF is greater than E here, the opposite thing. Okay, therefore 1 by say e to the power, here it is a E minus EF by 0 plus 1. You can see in this case the numerator is what? The numerator is negative here. Okay, therefore e to the power minus infinity will be here. Okay, therefore what does it become? 1 by e to the power minus infinity, because here it is a minus term, here it is a minus term will occur if EF written here. Okay, I am writing this thing, just wait, I am writing this thing. Minus, take minus common, because EF is greater than E, and write the EF on the front, and by 0 plus 1, and therefore it will become 1 by e to the power minus infinity plus 1. Okay, now this is okay, and e to the power minus infinity means 1 by e to the power infinity plus 1, therefore it becomes 1 by I think just wait, 1 by 1 by, it is infinity, and this is something by infinity is 0, that is 1 by 1. Okay, 1 by 1 term, that is 1. Okay, in the previous case what we have obtained, that the distribution function is 0 when our energy is greater than the Fermi energy. Okay, this is our energy. Okay, this is any energy. Okay, this is any energy. And in the second case, that f of E Fermi. When Fermi energy is greater than our energy is less than the Fermi energy. Okay, this will be 1. Okay. Now I am moving to the fact that when say it is point C, the point C, when E equals to EF, okay, this greater than less than 2 term, and this is the equal term. Okay, E equals to EF. Therefore, f of EF here it will be f of EF here, because E will be replaced by EF. Okay, and here will be a e to the power E minus EF by KT term, and here it is a plus 1. In our case, the numerator will be 0. That 0 by KT plus 1. Okay, T approaching towards 0, not actually 0. We cannot approach the absolute temperature. It is theoretically possible only, not actually. So, for very close to the temperature of absolute 0, and the denominator of the power of the exponential term will be will not be equal to 0. Therefore, we can write this thing at 1 by e to the power 0 plus 1. Okay, because t is not equals to 0, but okay, it is nearly equal to 0. Okay, approaching towards 0. That in this case, it will become 1 by 1 plus 1, that is half. Okay, this is a heavy claim. At Fermi temperature, this is half. So I am concluding these things, that when no, just wait, f of E is equals to 0 when E is equals to E, that writing epsilon, E is greater than EF, equals to 1 when E is less than EF, and equals to half when E is equals to EF. These are the 3 conditions that we have obtained previously. Okay, these are the box, these 3 things. These are the basis of the Fermi-Dirac statistics. Okay, you need to remember these things. So graphically, I am plotting this graphically. Let's make a graph. This graph will be a very important graph to remember. Okay, so graphically we can see just wait, I am drawing the graph. Just wait for a second. Okay, just in choosing colors, I used to fumble in each and every time when choosing colors. Okay, this is what, this is 1, and this is equals to half, and this is 0 here. This is f of E axis, and here it is energy axis. Okay, now moving to the graph. Okay, moving to the graph. Just one second. Sorry for the external noises. Okay, just wait for a while. Okay, now you can see the graph. The graph says that these are the energy scale, this is the energy scale. When say this point, I am writing this point as, say this point is our EF. F. This is our Fermi energy, okay? And this cut on this point, okay? You can see this thing that I'm. Okay, this is the graph. You can see from the graph that at Fermi energy, I'm making at Fermi energy, the occupation value, occupation index is what? That this is the distribution function is what? Distribution function is half. That what we obtained in our case, okay? Less than Fermi energy, this is the region where our energy is less than Fermi energy, okay? Less than Fermi energy, the region filled with, say, from this point. I am drawing this thing, but actually this point is left to the green point, okay? This green dot, left to the green dot, is E less than EF, okay? In this region, E less than EF, you can see the value of the distribution function is 1, and in the heavy region, that E is greater than EF, what is the value? The value is 0, okay? This is the E greater than EF, okay? This is the value 0. Just wait. This is in the E greater than EF zone, okay? So I am zooming this thing. You can check this thing out, okay? This region is called, this is the EF region. This point is the EF point, okay? This is one and only single point, okay? and this is the E greater than EF region, okay? And you can see from your theoretical approach that what does it become, okay? So this is the Fermi distribution function, okay? Now I am moving to the deviation term, okay? Just one second. Just to check, let me check this thing out, what is remaining, okay? Now I am making graph, and this graph will be applicable for each and every. Let's just wait. This is the graph will be like similar to the Bose-Einstein graph, okay? This is the higher energy. This is the temperature scale. This is what? This is the temperature scale. In the temperature scale, say you have some points. This is absolute 0. That say that is T equals to 0 Kelvin, and say you have, this is T is less than Fermi temperature. Say a particular critical temperature is called Fermi temperature, and this is T is equals to TF. That you have the Fermi temperature at, this is called Fermi temperature. This is the point T is greater than Fermi temperature, and this is the point where T is very greater than T Fermi, okay? Okay, now this is our say this is our normal temperature. Say this is 32 degrees centigrade. This is, okay? In this temperature, all the gases, all the particles, whatever it is, are non-degenerate, okay? Are non-degenerate. That means they can have different energy values, okay, for different states. And this is in this temperature, it becomes weakly degenerate, okay? Weakly, this is K. Weakly degenerate, okay? That some particles are degenerate or some not, okay? This is called the Fermi temperature. This is a critical point. I am not, this is Fermi temperature. We'll be calculating this thing, okay? This is called Fermi temperature. This is Fermi less than the Fermi temperature. This is the system becomes strongly degenerate. Degenerate means they all are proceeding towards the same energy level, okay. And this is the at 0 Kelvin the gas becomes very ultra strong, okay. Ultra strong degenerate, ultra strong degenerate, okay. This is the case you have to remember. This is the Fermi Dirac statistics, okay. And now I am moving to the, say, just just 1 second, just 1 second. Okay, let's calculate how to calculate the Fermi energy at 0 Kelvin. How to calculate this thing? This is a easy approach. We have done in our previous lecture, okay. How to calculate Fermi energy? Make a heading. How to calculate Fermi energy? In case of calculating the Fermi energy, we will start from the total number of particle formula. That is, our total number of particle is what? N equals to integration dn. Okay, what is dn here? Dn is the number of particles in the energy level, in the energy interval E and E plus dE. Therefore, dN will be replaced by, say, NE dE. Okay, this is the total number of particles and this is the energy interval. Okay, so the total number of particle can be replaced by FE GE dE, because distribution function is given by FE is equals to NE by GE. Therefore, from this formula you can easily write NE is equals to FE times GE. Okay, so this is that I have written. So our distribution function, Fermi energy, how to calculate the Fermi energy at 0 Kelvin temperature. Okay, just make this point correct. So we have our distribution function. We have our distribution function. What is our distribution function? Our distribution function is given by f of e equals to 1, f of e equals to 0, f of e equals to half. Okay, f of e is equals to 1 when this is the condition that we have did in the previous topic, and we know our density of state is what? GE. G is given by the total number of microstates, say d omega by dE. Okay, total number of microstate per energy interval. Okay, this is the definition of our this thing. Okay, GE, density of state. Sorry, I have forgotten this thing. So first we need to calculate our omega, number of microstates. Okay, number of microstates. What is our microstates? See, omega, it is, say our system is a continuous system. This is the spin degeneracy, and here it is a, say I am doing in, not doing 3D 4D. Okay, anything 3D 2D, anything. dfq 1 by h of dfq dfp, and in case of 3D, f will be what? F will be 3D. So omega will be what? Omega. This is a function of energy also. Okay. Omega will be Gs times 1 upon h cube double integration d cube q d cube p. Okay, we know how to calculate this. Gs is equals to this. First integration is on q, second integration is on p, and this term integrated and give v, the volume of the container. Okay, so this is d cube p will be given as 4 pi p square dp. Okay, we have did this thing many times. Okay, so how to calculate this thing? Now I am moving to the fact that this is omega. Now say E is equals to what? E is equals to p square by 2m, and in this case p square is equals to 2me, and from this thing 2p dp is equals to 2m de, and from this p dp, from this just wait, dp will be what? dp will be mde times p. P will be what? mde, here it is, and p will be root over 2me. This is from this thing. Okay, p is 2m root over 2me from this thing. So this is our dp. Put this thing here. Omega will be what? We have did this thing. We have did in case of bosons also. There will be a 4 pi terms out of the integration, and p square will be what? 2me times dp value is what? mde times root over 2me. Okay, make sure that the constants are out of the integration. That I'm taking the constant out of the integration, that 4 pi mp upon h cube, and here it will be a e power half and d. You can write this thing as epsilon. Okay, epsilon and e are same thing in case of this. So this is our omega. So what is our d omega by? This is our ge. What is our g? ge is equals to first derivative of the omega with respect to the energy, and you do not have to perform this differentiation because this differentiation will be acted on this integration, and integration and differentiation on acting with each other, they cancel each other. Okay, you can remember like this, not cancelling each other. So these are the opposite things. Okay, 4 pi mb upon h cube, here it is a e power half and de. Have I mistakenly done anything? Just wait for a second. Here it is a, I think here it is a root over 2m term. Okay, root over 2m term. Root over 2m. Here it is a extra root over 2m. Extra root over 2m. Okay, now the total, we have found our ge. We have found our ge. This is our ge, and the value of the ge is this. And now we are moving on our number of particle expression, that the total number of particle is what? Total number of particle is given by say, what is our total number of particle? That f of e, g of e, and d of e. Okay, this is the difference. This is the integration and on energy, and the energy value can span from 0 to infinity. Okay, so I am writing this integration like this, that the energy is from 0 to infinity. Okay, 0 to infinity, and from 0 to infinity, say in the very middle you have some sort of energy called EF. Okay, and this will be another limit from this. Let's break the integration to these two limits. Okay, these two limits, so it will become 0 to EF. Here it will be FE, GE, DE, and plus EF to infinity, FE, GE, DE. Therefore, we know the value of FE. We know the value of FE in the interval EF to infinity. That is, our energy is greater than EF, that is our energy is greater than EF. E epsilon are the same thing, okay? EF. In this case, what is our distribution function value? Our distribution function value is 0. Therefore, this term will be 0. And only this term will remain. Okay, the remaining term will be 0 to EF. FE will be what? 1. Because in the interval E less than EF, you have distribution function f of E is equals to 1. Okay, it's 1. GE will be what? GE is from our this expression. Put this GE from this. This will be GS 4 pi V by H cube root over 2m times m. Okay, here it is a e power half d. Check this thing out. Okay, this is the total number of particles. So the total number of particles will be opt out the constants from the integration. 4 pi V root over 2m times m upon h cube, and here it is e power half dE and 0 to EF. Now I'm done, and this is n. Perform this integration to obtain the value of number of particles. N equals to GS 4 pi V root over 2m times m upon h cube, and under perform this integration we will be getting, say, this is a 3 by 2 term, and the denominator 3 by 2, that will flip into 2 by 3, and EF power 3 by 2. I think this is correct. This is the value of the total number of particles. Now write this thing as okay, this is the total number of particles. This is the value of total number of particles in case of Fermi-Dirac statistics. Okay, in case of Fermi-Dirac statistics. Now obtain the value of EF from the above equation. What is the EF value? Will be what? EF, first I am doing the EF to the power 3 by 2 will be what? EF to the power 3 by 2 will be NH cube. Okay, NH cube, 3NH cube, and here it is a 8, I think so, just 8 pi V root over 2m times m, and here it is a GS term. Okay, I am correct, I think so. And EF will be what? EF will be, this is power 3 by 2 term, and when the power 3 by 2 will be applied on the right hand side, it will be flipped into 2 by 3. That will become 3. I am writing this in a fashionable manner, that is say I am writing n by V times 3 by 8 pi, and the other things h cube by, say, GS m to the power 3 by 2, and here it is a root 2. I think I am correct, and here it is a power of 2/3. Okay, you can see this is our Fermi energy expression. If you can remember this thing, then try to remember this formula. Okay, try to remember this formula if you can remember. Okay, try to remember this formula. It is not necessary to remember this formula each and every time. We are just interested in the dependency. What is the dependency? This is what I am replacing this thing by rho. Okay, because this is the number density, number of particles per unit volume, number density. So EF will be what? Proportional to rho to the power 2/3. Okay, and EF will be another, there is another function, that is number of mass of the particle. It becomes a 1 by m, because it has power 3 by 2 and it has very outer power is 2 by 3. That will become cancel with each other, that is EF proportional to 1 by m. These are the two dependencies. Okay. This is in case of 3D. In case of 3D. So I am doing this thing in case of 3D, and your homework is to do this thing in 2D. Do this thing and send me on WhatsApp. Okay. Now this is the value. This is the dependency, and also this is the Fermi energy calculation in case of this thing. Now I'm giving the general dependency. So general dependency will be what? General dependency. In calculating these things in case of various competitive examinations, you will be asking for, say, you will be given a dispersion relation. Okay, dispersion relation. Say your dispersion relation is given by E equals to alpha PS. In case of giving this kind of E, or sometimes it may be written like this, E proportional to P to the power S. Okay. In case of giving this thing, the Fermi energy will be proportional to rho power. This is the number density. It is S by D. This is the dimension. This is what? This is the dimension, and this S comes from the S here will be given. Okay, so remember this very important formula. This is a very important formula. Questions are directly asked from this formula. I am giving an example of this formula. Okay, example. Say energy is given as E is equals to P square by 2m. P is what? P is our momentum. Okay. So from this formula you can see that energy depends on the second power of P square. Therefore our S will be what? Answer. Our S will be 2. Okay. And you have been asked to determine the rho dependency of energy with rho in 3D. Dependency, write this thing. Of number density with the energy. Dependency of number density with the energy in 3D. This is your question. So in our case, S is equals to what? S is equals to 2, and in case of 3D, D is equals to what? 3. Therefore, the Fermi dependency of the number density with the Fermi energy. This is Fermi energy. Okay, will be equal to E Fermi is proportional to S is or what? 2. This is 3. This is your answer. Okay, this will be given to your options. Okay, this is what we called the Fermi energy. Okay, this is what we call the Fermi energy. Now our next topic is called the 0 point energy. Let's make an heading that 0 point energy. Okay, what is 0 point energy? It is the energy at energy of the system T equals to 0 Kelvin. Okay, so what is in case of calculating the energy? We know, say this is E0. I am writing this thing as E0 equals to what? Equals to integration E times NE dE, because NED is what? The number of particles. E times dN, you can write this, E times integration dN, and then replace dN by E times NE dE. Okay, so replace this NE by FE and GE is E times FE GE, and here it is a DE. Now the same treatment you have to do. Say it is E, this is E0, right? In this E0, E is equals to 0 to E Fermi. The first integration will be on F of E GE DE, and the second integration will be 1 EF to infinity, and here it is E FE GE and DE. Okay, now this term will be 0 because the distribution function is 0 in case of this thing. Okay, it's the energy greater than EF, and in case of energy less than EF, you have FE is equals to 1, so replace this FE by 1. Okay, you will be getting E times 1 times GE is what? GE is in our case GS 4 pi V upon H cube. Say have root over 2m term. I think check this thing out. Okay, E to the power half, and here it is a D. I think no more term in this thing. Okay, so this is the E0, and now what does it become? Opt out every constant GS into 4 pi upon H cube root over 2m times m, and inside the integration there will be a E to the power 3 by 2 term, because here it is a E and here it is a E to the power half. Okay, now make this thing correct. Say GS equals to 4 pi V by H cube root over 2m times m, and here it is, after solving this integration, it will become 3 by 2 plus 1 means 5 by 2. This is 2 by 5 times e to the power 5 by 2. Okay, this is the 0 point energy. Okay, in case of Fermi Dirac statistics. Okay, this is the 0 point energy. Okay, just now the relation between the 0 point energy and the Fermi energy is what? The relation between 0 point energy, and I am giving the between E0 and EF, 0 point energy and Fermi energy is what? I think you know the expression for E0 and EF. E0 and EF, and just wait. I am dividing the E0 by n. It will give EF by 5 into 3 from the equation of, you know what is 0, you know what is F, put this thing from. Okay, and it will give him rise to the expression for the relation. Okay, 3 by 5 EF. This is the relation of E0 equals to what? E0 equals to 3 by 5 EF in case of 3D. In case of 3D, the general dependency will be what? From the dispersion relation, general dependency will be E0 equals to D by D plus S into EF. Remember this formula. You can do in case of any dimensions. Okay, here D is what? D is the dimension and S is the dependency. Okay, S is the power of the dispersion relation, the power of the momentum. Okay, so this is the general dependency. Okay, now how to calculate the 0 point pressure? 0 point pressure will be what? Now moving on to the topic, say 0 point pressure. 0 point pressure can be calculated from the relation of energy and pressure. Okay, we know total energy is given by what? Total energy in case of 3D, it is 3 by 2 nkt. This is the mole, this is the number of particles. Okay, this is the mole number of particles. Okay, E is equals to what? 3 by 2 nkt. We know PV is equals to nkt. Okay, this means it will become 3 by 2 PV. E equals to what? 3 by 2 PV. When energy is equals to E equals to E0, then P automatically P will be what? P0, and replace this thing on the above formula, on this formula. This will become E0 equals to 3 by 2 P0 V. Therefore, P0 will be what? 2 by 3 E0 by V. This is the 0 point pressure. Okay, remember this formula also. Sometimes question asked directly from this formula. Okay, and the 0 point pressure and the Fermi distribution, Fermi relation will be what? We know, say 0 point pressure, and we know what is E0. Say 2/3, and in our case, what has become here? Say 3 by 5 EF here, and put this thing 3 by 5 here. This is the relation between 0 point energy and 0 point pressure. 0 point pressure and Fermi energy relation is what? 3 by 5 and E Fermi. Okay, this will become 3 goes with it, 2 by 5 E Fermi. This is the 0 point pressure and Fermi energy relation. Okay, write this thing on your copy. Okay, so Fermi temperature will be what? And the next is Fermi temperature. We know the Fermi energy, any energy, Fermi energy at 0 Kelvin, say Fermi energy at 0 Kelvin is proportional to what? Not 0 Kelvin. Fermi energy is proportional to Fermi temperature. Okay, that the energy will increase and it will giving rise to the temperature. So EF will be what? Equal to KTF. Okay, this K is what? This is the Boltzmann constant. So Fermi temperature will be what? EF by K. This is the Fermi temperature relation. Okay, calculate the Fermi momentum. Next Fermi momentum. Fermi momentum will be what? Say you have energy is equals to P square by 2m, and so replacing this EF, and this will be replaced by PF square by 2m. So PF will be what? PF will be root over 2m EF. If it has been asked for the 0 Kelvin temperature, then put 0 on the expression of the Fermi energy. And this is all. Okay, and this is all Fermi. Now I'm moving to the Fermi wavelength is what? Fermi wavelength is from the de Broglie equation. We know lambda equals to h upon p. This replacing this lambda by lambda f, and h is constant, and it will be replaced by p of f. We know the Fermi momentum. Put this Fermi momentum here. What is our Fermi momentum? H upon root over 2m EF. This is the Fermi wavelength. Okay, this is the expression. So writing this thing here. So, lambda. This is a important relation. Is equals to h by root over 2m EF. Fermi wave vector is what? Next point. Fermi. These are small points that you have to remember, and you do not have to remember precisely, because you are able to calculate each and everything if you know the Fermi energy. So focus on the technique how to calculate the Fermi energy, and focus on the technique how to calculate 0 point energy. That's all. You do know this de Broglie equation or anything. Okay, Fermi wave vector. Fermi wave vector is given by, what is our wave vector? Wave vector is equals to k 2 pi by lambda. K is equals to 2 pi by lambda. In from the concept of from the concept of simple harmonic motion, we know k is equals to what? 2 pi by lambda. Therefore, replacing this by kf, 2 pi, it will be replaced by lambda f. Okay, we know the lambda f from our previous example. Say lambda f is this. This will become, say, 2 pi by h. Here it is a 2 m E Fermi. Okay, this is the Fermi wave vector expression. I am writing this precisely. Kf is equals to 2 pi by h root over 2m E Fermi. Okay, these are the expression for a Fermi wave vector. Okay, this is all, and you do not have to remember much more about these things. Okay, I am giving a expression for Fermi energy at non-zero. We have calculated the Fermi energy. This is the last topic, that Fermi energy at non-zero temperature. I am giving just the expression. You have to remember this expression, not going to the detailed calculation, because the calculation is quite critical calculation. Okay, Fermi energy at non-zero temperature. Non-zero temperature, that means T is not equals to 0 Kelvin. Okay, this is the expression. It will be written as EFT. Try to remember this thing. It will be applicable in various E Fermi at 0 energy and 1 minus 1 by 12, and here it is a pi kT by EF0 the power square. Okay, best. So this is all. This is the Fermi energy. Okay, at any temperature, any particular temperature. Remember this thing. Try to remember, not remember. I am just try to remember this thing. If it is possible to memorize this thing, try to memorize this thing also. Okay. So this is all. This is all about the Fermi energy, Fermi systems. Okay, and for your competitive purpose, this thing you have to remember. I think this video goes too much long, and I have to terminate this video. And on the next lecture, I will try to complete the statistical mechanics for your competitive examination purpose, any kind of competitive, NET, SET, GATE, whatever it is. Okay, and I think one lecture is remained. Okay, I have to check this thing. I think one lecture is remained to end the statistical mechanics section, and therefore we will be moving on to another section. Okay, so thank you for being with us.